Hey guys, I'm back with a new video. So in this video, let us complete the implementation of a linear regression model for our old faithful natural geezer dataset, for which we had started the implementation in the previous video. So first, let us write the method to train our simple linear regression model and to find the values of m0 and m1 in the equation y is equals to m1 x plus m0. So I will leave a docstring as comment and I will say method method to train our simple linear regression model to find the values of m0 and m1 in the equation y is equals to m0 plus m1 into x. So I'll define a method and I will name it as simple linear regression. This will take on the collection of our input variable and the predictor, which is the predictor, and the output variable for which we are going to predict. For a certain value of input variable, we have to find the duration after which the next eruption is bound to occur. So we had discussed the dataset in the previous video, so if you haven't checked out that video, the link for that can be found down below. So what I will do is I will define an array of the values of m that we will be computing successively. So I will define an array for that, intermediate m, and then what we need to do is we need to compute the values of m0 and m1 using a formula that we had discussed in the video on parameters and coefficients of the model, so how to predict them. So the link for that can also be found down below. Let me recall you the formula that we had discussed in that video. So the formula was m1 is equals to summation k1 to n and x minus x bar, y minus y bar, and in the denominator we have summation k1 to n x minus x bar whole square. So this is the formula for m1. For m0 we have the formula y bar minus m1 x bar. So do make a note of this formula. We will be using these formulas for computing the values of m1 and m0. Let me define some variables now. So what I will do is I will name a variable as m1 numerator sum. Okay, so let me show you why I'm doing that. So this term will be our numerator, so I will name it as m1 numerator sum, because we will be computing it successively and we will keep on appending, making up the numerator from each of the rows of the data set that we are having. And similarly, we will be computing value for the denominator using x and y's that we will be getting from those rows to compute the value for the denominator. So we will successively be building the values of numerator and denominator to get the value for m1. Okay, so this term will be m1 denominator sum. Okay, so let me define these two variables first. So back in my Visual Studio Code, I will define a variable m1 numerator sum, set that to 0.0. Let me copy this down and I will rename this as denominator sum. So m1 denominator sum. And what I will do is I will write a simple for loop. So for I in range 0 and till the length of our collection of input variables. So we'll be covering all of the rows of our data set and we are basically iterating over the collection of input variables. Okay, so first let us compute the value for m1 numerator sum for each iteration that we will be consuming. So m1 numerator sum will be m1 numerator sum. We'll apply the formula that we had discussed, m1 numerator sum plus, so I will say xi, which is the value for our input variable for the ith row, minus the mean value for the collection of input variables. So then I will multiply this, I will copy this and paste it here, and I will change this to yi. So the duration after which the next eruption will occur, which is the y, and x is your duration. Okay, so this is xi minus the x bar into y minus y bar, the same formula we are using. And then let us compute the denominator. So m1 denominator sum, m1 denominator sum plus, I will say xi, so the value of input variable, which is duration for the ith row of our dataset. So for the very first iteration, the value of I will be 0, then 1, then 2, and we'll be grabbing the values of x and y's to compute these numerator sums and denominator sums. Okay, so I've already made you visualize the dataset in one of the previous videos. Do check them out before working on this video. So xi minus np dot mean x, and as a formula can tell you, we have to raise this to the power of 2. Okay, so x minus the mean value raised to the power of 2. So let me add that. So 2. And now to compute the value of m1, it is very simple. We will say m1 numerator sum divided by m1 denominator sum. As simple as that. And to compute the value of m0, the formula is y bar, which is what? np dot mean. Okay, and we can pass y, and then m1, whatever m1 we computed, into x bar. So np dot mean x. Now we will add the values of m0 and m1 to our intermediate collection for your m's. So intermediate m dot append and pass it as an array m0 and m1. Okay, so intermediate, and then what I will do is I will finally return this as an array and m0 m1, and then intermediate underscore m. Okay, so let us try this out. So I will be making a call to the simple linear regression, and let us copy this line down. So now we have the values of x and y. I'll copy this out and I will pass this into our function invocation. Now this will give us the coefficients and intermediate m, and let us log the coefficients and intermediate m to the console. So what I will do is I will run the file and I will say python geezer.py. Okay, so this is done. Okay, so you can see these are the values for our m0 and m1, and this is the collection intermediate. Next, let us see how we can predict the response variable y in the case the interval before the next eruption, which is y, for new values of x, which in this case is duration of eruption, using the values of m0 and m1 that we have got. Now let us visualize the data using the scatter plot. So we'll be plotting a scatter plot to determine the relationship between the input variable and the output variables, both of which are continuous in this case. So I'll define a method, a render scatter plot, and this will take on the values or the collection of our input and output variables, because we will be working with a bunch of such points of our dataset, and we'll pass on xy and then the coefficients. So if we don't pass the coefficients, then by default it should have none. Otherwise we'll have the coefficients with us. Now I will say plt from the Matplotlib. So this is for use for plotting of our graph that we'll be getting. So I'll say plt.scatter, and then I will pass on the values for x and y, or the collection of our input and output variables, and I will pass another variable which is s, and set that to 2, and then I will say plt dot, I will define a label along the x-axis, so which is duration of eruption in minutes, and then I will copy this line, put this down, change this to y label. So plt.y label. So this is the time duration before the next eruption, and this is also in minutes. Now if we are having the coefficients with us, so if we do have the coefficients, we got the parameters of the model, in that case I will say, so I'll define a small x. So this is for a simple one instance, so I say x dot np dot linspace pass 1. So for the start of our line, then we will define stop. So x of -1, which is the last value for our collection of input variables. So the very last row, from the very last row we'll be getting the value for our input variable. Okay, so this is our stop point, and then I will say 2000. So we want 2000 such points, and then I will say plt.plot and x, and then I will define a method called as predict, which we will see later. So predict, this will take on the coefficients, and this will take on a value of x, and then let us define the line width 2. So you will understand all these terms when I will show you the scatter plot which gets rendered. So for now, just write the code, you will understand it later for that matter. And here we will write plt.show. So this is our method to basically render the scatter plot, the plt.show. Now in this method you can see that for each value of x, that is ranging from 1 to the last value. So we are basically picking on points, and then you are getting the values of x, the complete range of input variables. And for those x's, for single instances, we are using the predict method, passing on the coefficients and x, and we are trying to predict the value of the duration after which the next eruption should occur, which is our output variable. In this case, it is interval after which eruption should occur, or is bound to occur after some time. So it's a prediction. So let us define a method for that, which is called predict. I'll leave a docstring comment here, so it's a bit longer, so I will copy paste it here. So it's a method to predict the response variable, in this case interval before the next eruption, for new values of x, which in this case is the duration of eruption, not durations. Using m0 and m1, we have to predict the duration before next eruption from the duration of eruptions. Okay, so if a single input variable is used, it will predict the output variable for only that single variable. But if you are supplied with a list of input variable or collection of it, then it will give us a list of output variable for each input variable. Okay, so a method should be able to handle these cases. So let us define the method. So I will say def predict, pass on the value of coefficients, and then x, and then I will say m0. I will grab the value for m0 from coefficients array. So let us see. So here we got our coefficients, and which was of the form m0 and m1. Once you get the coefficients, grab the coefficients 0, and that will give you the value of m0. Coefficients 1, which is the second one, you will get to the m1 value. So I will say m1 coefficient 0, m1 will be coefficients 1, and then I will define an array of predictions. So now if a list of input variable is used, then get the prediction for each of the input variable that you are having in your collection of input variables. Okay, so we'll have to check for the type of x, so whether it is a list or whether it's a simple primitive. So if, so here comes the condition. Now here, if type of x is a list, so I will say list, not in strings, list. And then for each instance of a single input variable, for x in our collection of input variables, so I'm grabbing a value of input variable which is we are grabbing a value of duration in the collection of durations that we are given. So for x in x, I have to make a prediction. So I will say predictions, and each prediction that we'll make, we will append that to a predictions collection or predictions array. So m0 plus m1 into that specific value on which we are currently on. So if we are given a collection of input variables, we'll grab the first value of x, we'll make a prediction, then go to the next value of x, make a prediction, go to the next value of x, make a prediction, and each time we are appending the prediction to our predictions array, which is initially empty. And then once we are done with the predictions, we will simply return them. So come down here and say return predictions. And if we are working on a single variable, so rx is a single variable, or it's a single primitive value and not a list, in that case we can simply make a prediction. So I will leave a comment here: if a single input variable is supplied, that is the primitive case, and here I will say if a list of input variables is used, then we will get the prediction for each of the input variables. Okay, and now for the case of a primitive case where we have a single value of x, just a single value, not a list, we'll simply say y is equals to m0 plus m1 into x, and then we will return x or return y. As simple as that. So this is the method for making our predictions, and here we can use the method for each instance of x that we are having. We'll pass that to the predict method and we will get the prediction by our model. PLT is used for plotting. So let us see how we can run this. Render scatter plot and pass on x and y and the coefficients. And let us see what we get. So I think the plot should get rendered, and each time for each value of x, we should have a prediction getting rendered on the plot, on the scatter plot. So let us see if this works or not. And I will say python geyser.py. Okay, so yes, so finally our plot is getting rendered, as you can see. So we are using Matplotlib here, and you can see we are getting the x label, which is duration of eruption minutes, and the y label, which says time duration before the next eruption. Okay, so this is how we can plot the scatter plot. So this does work fine till now. Now let us see how we can finally make prediction for a new instance. Okay, a new instance means that we're given a duration. We have to predict after how much time the next eruption is bound to occur. Okay, and I will leave a comment here. So I will say making predictions. So first of all, I will print the final values of our coefficients. So final values of the parameters of the model, and I will say coefficients of 0 and coefficients of 1. And then last eruption duration. So I'll ask the user to basically supply us the last eruption duration for which he wants to predict after how much time the next eruption should occur. So I will say float. So we will convert the input value that the user supplies using the float method, and then input, and I will ask duration of last eruption in minutes. Okay, so the user will give us this, and then I will print the time it will take for the next eruption to occur in minutes. So in minutes, put a colon, put a comma, and I will say I will invoke the predict method, pass on the coefficients, and pass on the last eruption duration that we got from the user. And let us try the code now. So I will say python geyser.py. We got the plot. As you can see in the console, it is asking for the last eruption duration in minutes. So in minutes, I will let us give some value. This is our data set. And let us use the value 4.467 just to check out whether we are getting a value close to 74 or not. So I will put that value, press enter. And it says the time it will take for next eruption to occur in minutes, 81.403, so on. Okay, and let us try running this again and pass some unforeseen value that the dataset is not aware of. So I will say 4.2 or 4.402, so a value close to this, and press enter. So you can see we are getting a value that is somewhat closer to 80.7. So this is the duration after which the next eruption should occur. So if the duration of the last eruption given to us is 4.402, so this is something we have achieved till now. Now let us do the performance evaluation of a linear regression model. So we'll calculate the value of residual standard error and the R-squared value. So I will leave a comment as a doc string. Okay, not this. So I'll say performance evaluation accuracy metrics of the model, calculation of the RSE, and which is the residual standard error, and the calculation of R square. So I will leave a print. So I'll say new lines and accuracy metrics. Can't type. Accuracy metrics of the model. And now let me recall you the formulas for RSE and R squared that we had discussed in the video on performance evaluation metrics of the model. So if you haven't watched that video, the link for that can be found down below. The formula for RSS we already knew is RSS was actual value of y minus the predicted value, which we can say y cap, raised to the power of 2. And the RSE is 1 by n minus 2. So n is the number of predictors that are given in our dataset, under root into the RSS value that we are having. Now let us compute the value for RSE. So we will be using this formula, okay, and we'll be using NumPy library for computing this. So let me close this and let us write the code for this. I will define a variable called RSS and set that to 0. And then I will use a for loop for index in range 0, length of the collection of our input variables. And then I will grab the value for our actual y, so which is what we are getting from the dataset. So y, and pass on the index. So we get the actual value of y. And then we want the predicted y, okay? Because RSS is actual value minus predicted value whole square. So predicted y we'll use the predict method, just invoke the predict method, pass on the coefficients to it, and pass on the value of x, a single instance of x, single instance of your input variable collection for which you want to predict the value of y. And then we can say RSS will update the value of RSS plus and actual value minus predicted value, and raise this to the power of 2. I think we don't need double braces here. Just this would suffice. Okay, fine. So now the value of RSC will be, because now we have the value of RSS, we can compute the value of RSC. We'll say numpy and we'll use the square root method on it, and this will take on the argument for which we need to compute the square root, which is RSS by the number of predictors that we're having, which we can get from length. We'll say len and pass on the input variable collection -2. And now we can print the residual error. So residual standard error and RSC to print the residual standard error over the average interval. So I can say percentage residual standard, okay, I can't type, standard error over the average interval, put a colon, and I will say RSC upon np.mean, so the mean value for y, and multiply this, the entire term, I'll multiply this with 100. So RSC upon the mean value of y into 100, not 1100. So let us see what we get as output by running the python gizu.py. So we got the plot, and if I pass on some value, say 4.4, so we got the time after which the next eruption will occur, 80.68, and accuracy metrics of the model. So residual standard error is 5.914, and the percentage of residual standard error over the average interval is 8.3416, and so on. Now finally, let us compute the value of R squared before we end up with this video. So now I will leave a comment, a normal comment. I will say calculation of the R squared performance metric. So I'll define a variable TSS, set that to 0, and if you don't know the value for TSS, let me tell you what is the value of TSS. We have already discussed this in the previous video. So TSS is the actual value of y, okay, and minus not the predicted value but the mean value of y raised to the power of 2, okay, and we will be summing this up here, also summation, okay, to get the value of RSS, and for TSS we'll be summing this up over the entire data set, and this we will take on the actual value of y and the mean value for our collection of output variable, and for each value of y and the mean value we'll be able to compute on these values, and we'll sum them up through the complete data set to get the final value of TSS. So this is what we want to compute, and then we will compute the R squared metric. So let me close this and define a loop for this. So I will say for index in range 0, length of our collection of input variables, colon, and then we first need to grab the actual value of y. So actual y will be y and pass on the index. So currently in the very first iteration we are on the very first input variable, okay, so we will give the index for that, so for the very first iteration, and for this we will be able to compute the value of y, which is the actual value of y, and then we will say TSS equals to TSS plus actual value of y minus not the predicted value, the mean value, np.mean, pass on y, and raise this to the power of 2. And finally, to get the value of R squared metric, I can say R squared is, so let me tell you the formula for this, and do make a note of this. So R square, not RSS, R square, this is equals to TSS minus RSS upon TSS. And we've already seen this in one of the previous videos. If you haven't checked out the video, I definitely recommend that you check out those videos first before watching this video. You have to understand the complete concept to understand the entire implementation. So here I will say TSS minus RSS divided by TS, and then I will leave a print, and I will say leave a new line r square value colon, and then I will say r underscore squared. Now let us try to run the file to get the value of our performance metrics. Python geezer.py, press enter. So this is our plot, and pass on the value for the eruption. So I will take it as 4.4, press enter, and finally we are getting a value of 0.814. We are having residual standard error of 5.914 and r square value of 0.81146. So this was all about the video on the implementation of linear regression model on our dataset. So we wrote the complete code from scratch without using any library. So we are not using sklearn here, okay? And we will continue with the implementation of various machine learning algorithms in the next video, and we will write them from scratch. So if you like the video, do give it a thumbs up, and I will see you guys in the very next video. Thanks a lot, guys.